Welcome to solverfy.
Okay, in this problem we have a discussion as to why the wavelength of a helium atom would be much, much less than the wavelength of an electron if accelerated through the same potential difference. So if both of these particles are accelerated through the same potential difference, we can assume they have the same kinetic energy just by conservation of energy. So we're asked, why exactly is this wavelength of the helium going to be much, much less if they have the same energy? So to answer this question, we can simply look at the definition of a de Broglie wavelength for a particle with mass, which is h over root 2me. And, or rather, I should say, this energy is the kinetic energy. And this is just a simple result. And we can replace our kinetic energy with 2mev using conservation energy. The kinetic energy that the particle will have is just simply equal to the electric charge times the potential difference it moved through. So we see that there are kind of two effects here. Lambda, as the electric charge of our particle increases, we would expect it to have a smaller wavelength. But more importantly, as the mass increases, we would expect a smaller wavelength. The mass difference between a helium atom and an electron is going to be enormous, 4 or 5, maybe even 6 orders of magnitude difference. So that's really what's going to cause the wavelength of the helium to be much, much less than that of an electron. Sure, the amount of net charge also matters. The helium atom will have a larger net charge because it has a couple more charges than one electron, but the mass difference is really what's going to make the difference here. So option B is the correct option. We have a much shorter wavelength because the wavelength goes down as mass goes up. And that's the main result for this problem.